A little bit an overview of what I'm gonna do during this talk and this afternoon. I have just 1 hour this morning, so my goal was to do the first 3 points this morning. Not sure I'm gonna be able to make it, but we will try. And so the first part is an introduction to fully homomorphic encryption in general, and the second part is gonna be more focused on the scheme TFHE. So I'm gonna tell you a little bit what is fully homomorphic encryption. So I have already a question. How many people know already what fully homomorphic encryption is? Lots, okay, very good. Almost all the room. And then I'm gonna try to tell you a little bit the history of homomorphic encryption. Where did we start? Where are we going? And I'm gonna try to focus in the first part on homomorphic encryption schemes based on the problem LW. So very general introduction. And then, yeah, again, second part is going to be TFHE. So we will see this afternoon. Okay, so what is FHE? FHE stands, of course, for fully homomorphic encryption. And it's a family of encryption schemes that has classical encryption schemes allow you to encrypt messages and decrypt messages. So in my slides, encryption is going to be noted or visualized as this boxes, or sometimes a lock on the bottom or a secret key explicitly written. And well, the message is the thing inside, in this case, X. And when you want to encrypt, you put stuff in the box. When you want to decrypt, you take them out from the box. Very mathematical, precise. So the difference between fully homomorphic encryption and classical crypto, if we want to call it classical, is that homomorphic encryption allows us also to manipulate information while encrypted. So it allows us to do computations over encrypted data, which is not generally possible-ish in classical encryption schemes. So in particular, we can imagine we can do addition between ciphertext or multiplication between ciphertext, and the result is going to be a new encryption, a new ciphertext encrypting the addition of the original messages or their multiplication. Now, the operations in the plain text and in the ciphertext space are noted differently, because in the plain text space, well, they're generally what we are interested in are additions and multiplications, but in the ciphertext space, additions and multiplication can be something more complex than a simple addition or a multiplication. They can be a set of operations that we will see details later, but yeah, this is the idea. And so when we talk about fully homomorphic encryption, what we mean is that we want to possibly evaluate any function, not only just an addition or multiplication. We would like to combine them and evaluate way more complicated stuff. And again, potentially any function. So we will see if we are able to do it or not. Which type of plain text can we encrypt? Well, we have schemes that encrypt the bits, integers, reals in with certain precision. And we will try to see a little bit how to do both secret key and public key encryption. So we have two variants of homomorphic encryption. We can encrypt with the secret key and, of course, decrypt with the secret key, always decrypt with the secret key. But it's possible also to have public key encryption and, of course, secret key decryption as usual. So I will try to show you a little bit how does it work. Cool. But why is this interesting to do homomorphic encryption? Why we are passionate about it? Well, the reason is that it's kind of a solution for the many privacy problems that we have nowadays, especially with the cloud era we're living in. So in this magical era, we all have generally connected devices. You have phones, you have computers, so you access the internet quite a lot. And generally you interact with this cloud, well, it's represented by a cloud, but in practice is servers manipulating your data, storing your data and so on. And we interact with the cloud quite a lot. We send emails, we have social networks, we store our data, and it's nice. It's very practical. You can access your data everywhere in the world if you have an internet connection. So we're very happy about this. But there is a, when we manipulate data, it's important also to protect this data, right? And yeah, generally what happens is that classical crypto allows us to protect the data when it's in transit. So when we send the data to the cloud, we can put a layer of encryption. When we send it, well, actually we can use classical crypto to store data on the cloud as well. But the problem is that when we ask the cloud to manipulate our data, to do searches on our data, to, I don't know, modify our pictures, apply filters, or do whatever they want to do, the cloud needs to have access to the clear text information. So we need, it needs to access our data. So once it goes to the cloud, I mean, the channel is protected, but once it goes there, the cloud sees the information in clear. And so it manipulates it, apply, let's say, a function F, and it sends us back. And again, when it sends us back, the channel is protected by crypto and it's encrypted. But again, data on the cloud side is seen in clear, like your emails are seen by Google in clear in the end, and whatever service you use. And so that's a problem, because when this data is sensitive, it can be your medical data, health, financial data, I don't know, whatever data you can imagine is sensitive and you don't want a stranger to see it. Well, we need to protect it. And that's why homomorphic encryption is interesting. It's because not only you encrypt the data during the transit as before, but the functionality that I was explaining before allows the cloud to manipulate your data without seeing it. So it can apply this function F I'm using without knowing the message inside the ciphertext. And it can send you, of course, the encrypted result, and you, user, owner of the secret key, are the only person that can really decrypt this data in the end. So it's very practical because, yeah, practical and hopefully secure because the cloud learns nothing about your data. It's encrypted all the time. Also, there are in practice no data breaches, because imagine that an attacker accesses the cloud. If the data is encrypted, what does it steal? Randomness. I mean, they can if they want, but it's not reveal anything about your data. And also, the server location of the cloud becomes kind of irrelevant. And why I want to point out to this point is because depending on where the server is located physically in the world, you're going to have different regulations for privacy. Maybe in Europe, you know, we have GDPR. In other states, we have some other regulation. Somewhere else, we don't even have regulations. So if your data is not protected, well, you don't want to send it to wherever in a random location in the world. So with homomorphic encryption, whatever the location of the server is, again, the data will be encrypted. And so, I mean, they can manipulate randomness if they want, but yeah, no breaches, no data revealed, no private data revealed. Okay, it was a very quick introduction. Do you have any questions already? Yes.
Probably an obvious question, but here we're assuming that user is a legitimate user.
Yes.
But what if it's a criminal and now they're going to store some bad things in our server, and we want to have some assurance that over the things we're storing? Is there some trade-off we can make?
It's a good question. It probably depends on the security model you're dealing with. I don't know, when you say a criminal, you mean like...
I want to, I'm the service provider, I'm the cloud.
Yeah.
And I want to control what people are storing on my server.
You want to control scares me a little bit, but whatever.
Say I don't want like damaging pictures.
Oh, okay.
Horrible things.
Yeah.
How do can I encrypt it but still have some checks at some point?
Again, very, very good question, tough one. Okay, so I don't know if I'm the best person to answer this question, because you're going to legal stuff and I know not much about legal stuff. Well, theoretically, you could run checks, but they are homomorphic checks on the data. If you're the cloud, you can run a check on potentially, since you can do any evaluation, you could run a check on the picture. I don't know, run a machine learning algorithm, and the machine learning algorithm will tell you if the picture is it's something that shouldn't be stored. I don't know, some pornographic stuff, I don't know, stuff like this. We have machine learning algorithms that do this, that recognize some patterns in pictures. But again, the problem is that even if they run those algorithms, the answer is going to be encrypted. And the only person that can tell you what is the answer is the user. So yeah, I don't know if it's really possible. On the other side, you're encrypting your data, you're storing things encrypted. So the cloud doesn't have access to this stuff. So it's just storing, from his point of view, random data. So I don't know if there is a way to go against the cloud and say, hey, in your cloud, there was, yeah, I don't know. Yeah, sorry. I don't know if this answered the question. I don't have a better answer to this, sorry.
I just want to add to that one, actually. So maybe a more specific question. So do you have anything like, yeah, so can you allow like several keys? Can you allow like a multi-key? So assume that you have like a main user secret key, and then there's like a threshold key that is distributed for like some accountability party, like a governmental party or something like that. So can you actually have a multi-key FHE encryption with different accountability policies for different keys?
You can have multi-key homomorphic encryption, yes.
You can have like two keys and one of them will be threshold key.
I don't know. I think right now we have full threshold, but probably threshold is also possible. Need to double check. I need to double check. In case multi-key is possible, but I don't know. At least for TFHE, the solutions I know right now, but other schemes exist, of course. I think they are full threshold, so all the participants need to interact.
I see.
But I think there are solutions for even not full threshold. I will need to double check. I don't know exactly, but yeah. Okay. Yeah, go ahead.
So I was just thinking about this idea of providing the server a guarantee about what data you're storing on their server if they can't read it. Could you use some kind of verifiable encryption where you're proving in zero knowledge that the ciphertext or the message you're sending to the server satisfies some property without revealing what that data is?
Yeah, you can, but I don't know if you can do it at the level we're talking about. Might be very, very expensive. It's an open research area, I would say. It's theoretically possible, but probably very inefficient at the moment. Yeah. Where research is going on, so maybe in a few years will be possible. Okay. Should I continue? Okay, so a little bit of history. So we here are talking about homomorphic encryption in the last 10 years, I would say. But actually, the story is a bit older than 10 years. The first time the idea came out somewhere was 1978, where those three scientific people, Rivest, Adleman, and Dertuzos. Rivest and Adleman, you might know them from RSA, published a paper where they talk about privacy homomorphisms. And those privacy homomorphisms are sort of the idea of what we call fully homomorphic encryption right now. So it's pretty old as an idea. I mean, not pretty old, but like it starts dating a little bit. But the problem is that the first solution, the first fully homomorphic encryption solution was only proposed in 2009. So 31 years passed between the original idea and the first solution. So sometimes we can ask the question, well, what happened in the meantime? Why it's so hard to find a solution? And especially the question is interesting because in the meantime, we had something that was already partially homomorphic. So an example is RSA, as I was citing already. I suppose everybody here knows RSA. In RSA, you select two large primes, different one of each other. Again, this is the naive version of RSA. It's not the one that we use in practice, but yeah, it will make the job. So you choose two primes that are kept secret. You compute n p times q, you compute phi of n. Also, you choose a small quantity e that is co-prime with phi of n and smaller than phi of n. And also you compute d, which is the inverse of e modulo phi of n. So you publish N and E, and you keep secret P, Q, phi of N and E. So encryption, as you might already know, you do it by doing the message to the power of E modulo N, and you decrypt by putting the cipher to the power of D modulo N. I mean, I'm not revealing anything new. But what is nice for RSA is that if you take two ciphertexts encrypted under the same public key, well, and you multiply them, like you multiply C1 times C2 without knowing the message or the secret, this will produce a ciphertext encrypting the product of the original messages. So this is what we call multiplicative homomorphic encryption property. So yeah, RSA is homomorphic with respect to the multiplication, but is not homomorphic with respect to the addition. So that's why partially homomorphic, only one operation homomorphic, the other not. Again, RSA that we use, it's modified, so we don't use this naive version, but you see we already have homomorphic properties coming. And RSA is not the only scheme that is partially homomorphic. Similar properties happen in Elgamal, Payet, Goldwasser-Mikali. So those schemes are older than 2009. I think the last one was Payet in 1999. So why there was a block in finding something that was fully homomorphic. Also, we had some more homomorphic than partial solution. One of them is the solution by Bonego and Nissim in 2005. They had a scheme that was homomorphic for the addition and allowed you to do one single multiplication. So it was a bit more than partial homomorphic, but not there yet. Yeah, actually what we have, we had also, and we continue to have right now, are leveled homomorphic, which are the thing that is closer to fully homomorphic that we can have. And the fact that it's called leveled is because there are levels of something that we want to see what they are. And I'm going to try to explain you, I mean, the difficulty of fully homomorphic encryption by focusing on a level homomorphic encryption scheme. Yeah. So the one that I use always to explain the problem is the scheme DGHV, which was proposed in 2010, so 1 year after Gentry, by Van Dyck, Gentry himself, Halevi, and Vaikuthanathan. And the scheme is based on the approximate GCD problem, which is a lattice-based problem. And it's a scheme that I found very, very nice and easy and very intuitive to explain homomorphic encryption. So the original scheme, the basic version, encrypts bit messages, but it can be extended to whatever integer messages you want, I think. I don't know whatever integer, but to integer messages. And you choose as a secret key what we call P, a large odd integer. And in order to encrypt, you choose a quantity Q, which is an integer again, and is way larger than P. And also another quantity E that we call noise, and that is way smaller than P. So P secret, Q larger, E smaller. And the way you encrypt is very easy. You just multiply P times Q. So Q and E are your randomnesses for the encryption. And then you add the 2 times the error and then the message. So the encryption is extremely easy. It's just an addition and well, scalar multiplication. So to decrypt, again, is also very easy. If you know the secret P, you reduce modulo P, which takes away this part in theory. And then you reduce modulo 2, which will take away this part, and the message is what remains. Since we're reducing modulo 2, well, the message that remains is a binary message. And if the parameters are chosen correctly, this should be correct. But yeah, something happened if you want to use their homomorphic properties. So in particular, the DGHV has both additive and multiplicative homomorphic properties. If you in fact take 2 ciphertext encrypting, well, 2 messages M1 and M2 under the same secret key P, randomnesses Q and E should be random, so different potential. Well, you can add those 2 ciphertexts together and you can multiply them together. And if you solve a little bit the math inside, you will observe that C1 plus C2 becomes an encryption of M1 plus M2 modulo 2, so it's a XOR operation. And the C1 times C2 is an encryption of M1 times M2, which is in practice an AND gate. So this is nice, but there is a problem, and the problem, I put it in red for you to see it immediately, and it's the noise. So the part that is multiplied times 2. So what is the problem of the noise? The problem is that if the noise starts, you can see like in the addition, it grows, it kind of doubles. In the multiplication, it goes to the square of the original quantity. So it starts growing. And if you start doing operations, addition, multiplication, next to the other, one next to the other, well, the noise continues growing. And if at certain point, if it goes too close to P, the decryption might be incorrect. Because when you do the decryption, the reduction modulo P might take away part of the 2 times blah, blah, blah. And when you do modulo 2, the parity might not be respected, so the decryption is incorrect. And so the point is, if the noise grows too much, the decryption is incorrect. So you have to deal with this noise. And so the DGHV shows you the noise problem quite clearly, in my opinion. I hope you see it clearly. But I mean, the DGHV is just an example. We don't use it much anymore. But all the encryption schemes, homomorphic encryption scheme that we use nowadays have a similar problem with noise. So we always put noise during the encryption phase for security reason. And every time we do an operation, the noise grows. And again, if it grows too much, the decryption is incorrect. So there are 2 ways to overcome this problem. I mean, before Gentry, just one way, after Gentry, another one. So if you know the number of operations you wanna evaluate homomorphically, what you can do is set up your parameters large enough in order to fit enough operations in the noise thermometer. I'm gonna use the thermometer a lot. It's a thermometer that tells you how much noise is inside. And when we reach the red bar, it's red, so it's danger. So you can fix your parameters large enough in order to fit as many operations I mean, a limited amount of operations, but if you have to evaluate a limited amount of operations, you will try to set up parameters in order to be able to fit them, and you will do your evaluation, and in the end, you will decrypt. But if you don't know how many operations you have to do, because I mean, when we send the stuff to the cloud, who knows what is the circuit evaluated? Or when you have really a lot of operations, this solution is not valuable anymore. It's not practical anymore. And so Gentry proposes an alternative solution, which is like the final solution to the noise problem, or at least the only one that we know nowadays. And it's called bootstrapping. I will explain bootstrapping in the way I see it in my mind, and to give you a little bit the intuition of what is going on. So imagine that, yeah, you have this ciphertext, and the noise has already reached this red bar, and danger is screaming, and we cannot do any additional operation. So what would you do at this point? Well, if you have the secret key, you decrypt, the decryption gets rid of the noise, and you encrypt again. But the problem is that if we are in a cloud scenario, and the operations are going on in the cloud side, you cannot provide the cloud with the secret key. Otherwise, why are you encrypting in the first place, right? And so you need to find an alternative. I mean, you don't want the cloud to send you back the information. You decrypt, you re-encrypt, and you send. It's going to be a bit impractical. So you're going to do the following. You're going to try still to get rid of the noise by decrypting, but decrypting in a special way. So what you do is you take the blue encryption, the blue box, and you put it inside a green box. The green box is, again, homomorphic encryption. So since it's homomorphic encryption, there's going to be a little bit of noise related to the green box. It's very small because we are freshly encrypting. And let's say that your original ciphertext that is very noisy has become your plain text. So nothing happens. It's a plain text. We encrypt it and it's fine. But the noise didn't change. So now what you want to do, since the green encryption is homomorphic, you want to open, so decrypt, the blue box inside the green one. So to do that, you're going to provide the blue key, which is the secret key for the blue box, inside a green box. So now what happens? Since the green box is homomorphic, and since decryption is a bunch of operations, you're going to evaluate the decryption circuit of the blue box inside the green one. So you homomorphically decrypt the green box inside the blue box inside the green one. And so the result of this operation, what's going to be, is going to be an encryption of X inside the green box. The blue box disappeared because we decrypted, and the noise in the green box increased a little bit because we were evaluating homomorphic operations. So when you evaluate homomorphic operations, noise grows. But the point is that if after this operation, in the thermometer right there, in the green thermometer in output, there's still a little bit of space to do at least an additional operation, then you win because you build a fully homomorphic encryption. Because you can do operations. When you reach this point of noise, you do bootstrapping, again, operations, bootstrapping, and so on. And so potentially you chain as many operations as you want, one next to the other, and you build a fully homomorphic encryption. Yes.
I think you mentioned this before, but I'm in relation with this, but how is this better than decrypting and changing and fixing the noise in the plane?
It's not better in terms of performances. It's way worse actually than decryption because it's homomorphic decryption. But the difference is that you avoid communication. Okay? If you're in a user cloud scenario where the user is the owner of the secret key and the cloud is the guy doing computations, when you reach this point and you don't want to bootstrap, you need to send back your ciphertext in order to be decrypted and re-encrypted and sent back. If your model allows you to do this, you do it. But if you just want to send stuff to the cloud, make him do stuff and receive the result, and yeah, this is the...
How do you know that the noise is getting bad?
Good question.
I thought the one doing this was the owner of the ciphertext.
No, this is the cloud doing that.
Okay, now
and we are sending to the cloud the secret key encrypted because it doesn't need to see the secret. If you're the owner of the ciphertext, it means that you know the secret key, so you do it. But if you're the owner of the ciphertext doing computations, you don't need especially to encrypt. You can do the computation on your data in clear light.
So then how is it the cloud knows that the noise is getting bad?
So the way we predict that the noise is getting bad is by doing analyzing noise formulas, what we call noise formulas. So in practice, the noise at the encryption phase is parametrized. Generally is a Gaussian with some variance that we know. Keys as well are parameterized. We know all the parameters. And so we can build formulas that predict how much the noise is growing after every operation. And so, of course, you cannot say exactly where the noise is, otherwise the scheme will be broken, but you can say around, I mean, where we are a little bit about, how many bits of noise you might have consumed. And when you're approaching this dangerous point, you bootstrap. So you might be bootstrapping at the right moment, a bit earlier, or unfortunately, sometimes a bit too late. We try to build the noise formulas to be as precise as possible and giving you, let's say, high probability, a high probability that you're bootstrapping at the right moment. But yeah, it's probability, so you have to deal with it. Other question? Yes.
To continue this process, you need multiple bootstrapping keys then, because you're under the second.
Yeah. Not always. Sometimes you do right there, you do an operation that we call key switching. You switch back to the original key and you do a circle. It's not the only solution. You can have a chain of bootstrapping keys if you want. Or sometimes actually the blue and the green key can be the same key. So it depends on the way you're parameterizing your schema, but yeah, that's it. Any other question?
Leo on Zoom had his hand raised before, but it's down again now. I don't know.
Yeah, in fact, it was
Yeah,
exactly the same question. Maybe another question is,
Yeah, now I can.
Is there an interest of re-encrypting X within the green box, or is the noise too big? Because if the noise when you re-encrypt X within the green box is low, therefore you can just use only one bootstrapping key.
I'm not sure I understand the question. Can you rephrase it?
Here, if you want to do another operation, you will probably need a new bootstrapping key.
Yeah.
And my question is there an interest of blue encrypting X within the green box, decrypting the green box, and recover X within the blue box, so that you can use always the same bootstrapping key? Or is the noise with this operation too high?
So you mean like doing the bootstrapping in by inverting green and blue? It's the next step.
Yeah.
Yeah. Depends on your parameter, but what I was saying before to, I don't know your name. Actually, you can just do what we call a key switching in the green box. Go back to the blue key. The key switching is an operation that makes noise grow a little bit, and then do the bootstrapping in the same way. But again, sometimes you don't need the key to be different. It can be the same key. So yeah, but actually your question at the beginning, I thought you were asking something different, which is a little bit, this is very abstract. In practice, we never re-encrypt this. We go straight to this point, but well, well, it was just to simplify explanation, but like sometimes you don't even need to add this additional layer. You can go straight to the evaluation. And again, you can use the same bootstrapping key all the time. You just need a key switching key eventually to go back to the blue key. That's again, I didn't explain key switching key. Is going to be in the slides later, but yeah, hope this answered the question for now.
Okay, thank you.
Thank you for the question. Yes.
Hi, I'm wondering if two encryption box had the homomorphic also.
The which one?
Two encryption box has homomorphic also.
Yeah, both of them are homomorphic. I mean, the first one might not be homomorphic, but then you're doing transciphering, so it's something different.
If there are homomorphic feature property, why do we need to describe the blue box?
Why do we need to
describe the blue box? Because we can keep this and compare this.
Yeah, you can keep it in next round. I mean, you can do everything with the blue box in practice if you want.
I mean, why we need the decryption? Because it's a
because you want to get rid of the noise in the blue box, and you don't have any other way to reduce the noise in the blue box. Like this noise, the thermometer, you have to think that the thermometer is only growing. It never goes down. So only going up. So the only way to bring the thermometer down is to change thermometer and to get rid of the first thermometer this way.
But when we encrypt the green box, the thermometer down, right?
Yeah.
And for the
but you're fixing it in the first moment. When you put the thermometer, you decide where it starts. But when you start a thermometer, it goes up. It never goes down. It's a special thermometer.
But the thermometer of on encryption is the green one or the blue one?
So the one next to the blue is the blue. The one next to the green is the green. Well, the green color in the thermometer just to say safe. But yeah, this little one is the green one.
But when we compute an operation again,
yeah,
this one is green.
When we compute which operation again?
Like we add x with another y.
Well, you don't do x plus another y here. You do it here, and you use the green one. And before there were x plus y here. That's why the thermometer get up. So here you don't do x plus y. All the homomorphic encryption operations, you did them before, or you do them after. Here, you want to just get rid of the noise. Does it explain? Yeah.
A little bit. Okay, I will ask you like
Okay. Yes.
When you do your encryption in this green box, do you use the same public key?
No, not. I mean, depends. You might use the same.
This blue private key.
No, it might be different. Yeah, you use a different public key to do the green encryption.
Then what's the decryption key for this green box at the end?
A green secret key. The user, the same that use the blue secret key. So the user, the one that encrypts, in this case, has two secrets. One to encrypt at the beginning, and one to do the bootstrapping. And he interchanges those keys with bootstrapping. So here you're in the green key now, still belongs to the user. And imagine that we want to use the blue key again. You have this key switching key, which is in practice a blue encryption of the green key, and you go back. It's like a cycle. Keys encrypt one the other if you want, but all the secret key belongs to the user, and the cloud just uses this key, which is an encryption.
Can do the same operation with another green key of his own?
No. No, because if he uses his green key, I mean, in order to do this operation, he needs to know the blue key. And he doesn't have the blue key. He cannot encrypt the blue key. Oh, no. Yes.
So does so you've got some noise from encrypting in the green box, and then when you've got the green box with just X in at the end, there's more noise.
Yes.
So does this kind of mysterious, like internal homomorphic decryption thing increase noise, but it's just not as bad as if you left?
Yes.
Okay.
Yeah. Every time you do operations, the noises increase.
Including this decryption thing
Yes.
inside the green box.
Yeah. But the point is that the noise that was problematic was the one in the blue box.
Sure.
And this one, you get rid of it. Here, you've set up the noise low. With this operation, you make it grow. But again, you have space there to make more operation.
Better, yeah.
That's, and then, well, you do operation, you go back here, you imagine it as a
Yeah,
cycle.
yeah.
Well,
Yeah.
sorry, to make questions, what's the average efficiency of this? So how much noise you get in the end compared to the, how much space, how much slack do you have like in the end when you get a new noise?
It depends on your parameter. You
Yeah,
can,
but like just approximately, just one operation, you know,
you can set
lots
up,
of operations.
you can set it up for one operation of to way more operations.
So snarks have like several, you know, million gates, so 80 million gates. Can
No,
So you
80
can't do-
millions, I don't think we
Okay,
need to do
so-
this.
what's the order at least? So how often do you need to do bootstrapping? Like quite often.
Depends. There are solutions where you do just one operation in between the bootstrappings. There are solutions where you do, I don't know, 10 levels of applications, and then you need to bootstrap.
Right, anyway, case
Yeah.
it's one order.
No, it can be 1, 2, 3, 4. It depends on
Orders, but you can't do like can you do a million?
no.
Okay.
I mean, potentially you could, but your parameters explode, so it's not practical at all in practice. Oh,
Can we say that, for instance, the free space here has some, for example, relation with the security of the underlying encryption we are using because of this operations that we are the more secure encryption that you use, maybe you lose some kind of functions as a because in this decryption phase we are doing some kind of fully homomorphic thing on this decryption. And as a result, if you are, for example, the underlying encryption scheme is some kind of sophisticated and needs lots of operations, then we will lose this free space. But can we say that there is a connection between the security of the underlying encryption scheme and that the free space for the noise will get there?
there might be a link, but you can again adapt the parameters to keep the same security, increase the space afterwards. So you can imagine that your security is always at least lambda 128 generally, and yeah, every time you do operations, you don't decrease security. The security stays. What you can do is, I mean, in order to have 128 bits of security, you can fix I would say, an infinite set of parameters that will allow you to have the security. Those infinite sets of parameters allow you to do more or less operations, maybe more efficient, less efficient. So it depends on your application you set. And okay, may I continue? So last observation on bootstrapping. Bootstrapping, yeah, it's a very nice operation. It solves the noise problem, but it's very, very inefficient because you're evaluating homomorphically the decryption circuit. So it's very, very inefficient. And so sometimes we ask ourselves, do we need to bootstrap all the time or not? And I'm going to give you the rule of thumb, which is, I don't have an answer. The answer is it depends on the circuit you want to evaluate, but at least you can follow this guideline. If the circuit you want to evaluate, if the operations are a small number or small in terms of multiplicative depth in generally, and especially if the circuit is known, so you know how many operations you want to do, then you can use a leveled approach. So again, set up your parameters in order to have enough space in the thermometer and be able to do operations, all the operations you want without doing bootstrapping. But if your circuit is deep, so you have many, many operations, or it's unknown, so you don't know how many operations you want to do, then a bootstrapping approach might be better. And the reason it's better, especially for deep circuit, is that in the level approach, the larger the circuit you want to evaluate is, so the more operation you want to put in this thermometer, the larger the crypto parameter needs to be. And when the parameters grow, also the cost of operations grow and the memory consumption and so on. And so at some point, if your circuit is really deep, your parameters will explode. So potentially you can put thousands of operations, but yeah, it's not going to be contained in a computer or in a server. So at some point there is a limit, a physical limit in terms of, well, memory or execution time. I mean, we don't want to wait 10 years to have a computation. And so in that case, well, if the circuit is small, go ahead on this level approach. But if your circuit starts being very deep, using bootstrapping might be worth, even if bootstrapping is a bit costly. Yeah, so you don't have definitions. Yes. Yeah. Nancy, yeah.
Hello, ma'am. Actually, I want to know that what is mean by leveled approach?
Okay. When I say leveled approach, means that you set up your parameters in advance in order to be able to support a fixed amount of homomorphic operations. Actually, in leveled approach, you could use bootstrapping as well. But yeah, it's overly complicated to, I think, explain. Let's say you don't do bootstrapping. You set up your parameters in advance, and in order to be able to support a limited amount of operations, the one that you want, and you don't need to bootstrap.
Okay, thank you.
Of course. Okay, so this slide is just a summary. I think I still have a bit of time. So again, to summarize, in 78, initial idea. In 29, first fully homomorphic encryption solution with the bootstrapping by Gentry. And then after this solution was proposed, well, research started producing so many things. We had the DGHV that I was talking about before in 2010, which is based on the discrete approximate GCD problem. In 2011, we start seeing fully homomorphic encryption solutions based on LWE, which are the ones that we really focus on nowadays. And the first one was proposed by Brakerski, Gentry, and by Kutanatan. Sorry for the pronunciation of their names. Again, LWE continues and we still look at it. In 2012, we also had the homomorphic encryption solutions based on N-true. The LTV solution, I think, was broken in the meantime, but right now, schemes based on N-true combined with learning with error are coming back. So it's very nice to keep an eye on them. And in 2013, actually, we continue on the path of LWE-based scheme, and we have the GSW solution, so Gentry, Shahai, and Waters. And so, yeah, in the first part of my talk, I'm going to try to give you an idea of what is going on there and what are the differences between the two. And then, yeah, more solution based on those approaches came later. 2012, we have the scheme BFD. 2014, few goes in the path of GSW by proposing a very fast bootstrapping. And 2016, we have CKKS again on the more leveled approach, and TFHE, which initially improves the gate bootstrapping of few and then goes to a broader direction that still is in the fast bootstrapping branch. So I would like to clarify this. When I say leveled scheme, I don't mean that they don't do bootstrapping. They can be bootstrapped, and bootstrapping exists. It's just that bootstrapping is very costly for those schemes, and so they generally prefer to use a leveled approach. So that's why I will call them leveled, but they are not. They are fully homomorphic encryption, so they can be bootstrapped. The GSW branch initially was considered less efficient, but then the fast bootstrapping was proposed, and nowadays the one that is not afraid of using bootstrapping as much as they can. So yeah, let's say that there are those two major approaches. I mean, I put in lots of stuff under the carpet, but just to give you an intuition of what is going on today. So I'm gonna continue on this part. So I'm gonna focus in this first part of the talk on those two guys. In the second part, I'm gonna do more deeper in TFHE. And tomorrow, Anna is gonna go in this direction. Yeah.
Are there any known solutions?
Good question. Some solution appeared, not based on lattices, based on different problems, but to the best of my knowledge, they are not valid in terms of security, especially. And so I don't know all of them, but the ones that I'm aware of were broken in terms of security. So for now, I would say no. But hopefully somebody will propose it and we don't have the noise problem. So who knows? But yeah, for now, no. Okay. I will try to, in the next 10 minutes, to start going right there, but I will not have time to finish this section, so I will continue this afternoon. Yeah, so I'm gonna enter a little bit on the FHE schemes based on learning with errors. I will redefine learning with errors, but it was already defined before so many times. So I'm going to go very quick on this one. So LWE is a hard problem on lattices proposed in 2005 by Oded Regev. It sets up, I mean, the description I'm going to use is this one. I hope is accurate enough. So you have a secret that in my case is a vector of n elements, integer elements that can be random, small secrets, can be many stuff, but let's say secret. You choose random set of elements A that I will call mask in the rest of the talk, and a little Gaussian error, and then you build B equal to the product of the secrets times the mask plus some error, and that's it, modulo Q. And then, yeah, you call, I'm gonna call the list of A and B's LWE sample. The secret stays secret, the noise stays secret. And then, well, the hardness of learning with errors said, very not mathematically clean, but just again to give the intuition. Well, it's hard. You have two problems. You have the decision problem that says that given as many samples as you want, LWE samples or random samples, it's hard to distinguish between them. So in practice, this means that LWE sample look like randomness. That's why I say when the cloud sees your data, looks randomness. There is also a computational problem that says that given as many samples as you want encrypted under the secret key S, it's going to be hard to retrieve the secret key. That's it. So security of the LWE is based on this. And well, a few years later, also the ring LWE version appeared. So we are on rings, not anymore on integers. And both of the problems are used to build the fully homomorphic encryption. Again, I suppose this was already covered. So in homomorphic encryption based on LWE, we use many types of ciphertexts. The first one are the LWE ciphertext, the one that I call LWE ciphertext. And in LWE ciphertext, you can encrypt or on the most significant bit or on the least significant bit. What does it mean? I will try to explain. So the message is a message that we can say is in ZP, where P is an integer. And your ciphertext is going to be in ZQ to the power of n+1, which is exactly the size of an LWE sample. So you have n elements in the mask and one additional element. So generally, P is smaller than Q. So in order to encrypt the message, you will set up a secret key. In all my slides, I'm going to use binary secret keys. It's not mandatory. They can be ternary. They can be Gaussian. They can be sparse. For simplicity, in my slides, I'm going to keep binary, uniformly distributed binary secret keys. So you choose your mask, so your random elements in ZQ, and then you build B in the same way as you build your LWE sample. It's just that in this case, you're going to use A times S plus the error as a mask to your message. And in particular, your message, you rescale it by this quantity delta that is generally about Q over P, or in any case, a quantity that we know. So in order, the error is Gaussian, of course. So in order to decrypt, what you do, you start by computing B minus A times S. If you have the secret key, you can decrypt, so you can compute this operation. If you solve the math right there, you notice that this is equal to delta M plus the error. And once you have delta M plus the error, you will rescale by delta and round. And if the error was smaller than delta over 2, this operation is correct. So you decrypt correct. So some of the schemes that use this most significant bit approach are BFD, CKKS, and TFHE. I'm putting many things under the carpet by saying this because CKKS is slightly special, but information is in the most significant bits, and the least significant bits, there is error. So this is the idea to keep in mind. So why does it work? You can, keep this image in your mind. In the most significant bits, you have the message. In the least significant bits, you have the error. And if the error approaches too much the message might be compromised. So you want to always keep it under delta over 2. Otherwise, yeah, decryption could be incorrect. So this is just to give you a visual intuition of what is going on in delta M plus the error. So as I said, like you can encrypt in the most significant bits, but you can also encrypt in the least significant bits if you want. And this is the approach used by BGV as instance. So the encryption is exactly the same, but there's a little difference. Before you had the error plus delta M. Right now you have the message in the least significant bit, and you rescale the error times P, where P is the plain text modulo. Everything else is the same, apart, of course, for decryption. The first part of decryption is the same. You compute B minus A times S. By solving the math, you will see that it gives you P times the error plus the message. And so right now, to retrieve the message, you will do similarly to what we did in DGHV. You reduce modulo P, and you retrieve your message. So again, this is more the approach used in BGV. And visually, you can see it this way. The message is in the least significant bits. The error is in the most significant bits. It grows this way. And if it reaches this part, the reduction modulo Q will make it go on the other side and compromise the message. So always keep it limited. So in the rest of the talk, I'm gonna focus on most significant bit schemes, but mainly the majority of the observation I will do are also valuable for the least significant bit encryption. So yeah. I still have 5 minutes. Okay. Okay. So what are the, I show you how you encrypt, how you decrypt with secret key. What are the homomorphic properties of LWE? Well, LWE is additive homomorphic, meaning that if you add the two ciphertext under the same secret key together, and if you solve the math behind, or you trust me, the output is going to be a new ciphertext encrypting the addition of the original messages under the same secret key with the noise that has grown a little bit additively, roughly additively, actually additive. I mean, by consequence, is also homomorphic with respect to the multiplication time as small constant. And you can add a ciphertext within itself many times, and it gives you an encryption of the ciphertext time the many times you add it together. So again, the constant must be small because the size of the constant affects the noise growth. So if the constant is larger, the noise grows faster, and you have to be careful. You don't have multiplication for now, so it's not fully homomorphic, but it will become at some point. Something that it might be worth citing, as I was saying, is public key encryption. I just show you how to encrypt with secret key, but you can also encrypt with public key. And so what is going to be the public key in this case? Well, thanks to the fact that LWE is homomorphic with respect to the addition, your public key is going to be a list of encryptions of 0. So in practice, the owner of the secret key owns the secret key and keeps it secret, of course, and it publishes many encryptions of 0. So in practice, they are built as encryptions of 0. A is random, B is equal to A times S plus the error, so 0 message added. And then what you do to encrypt? Well, the person that wants to encrypt selects some small randomnesses, generally distributed as the secret key or following a different distribution, generally very small. And then he adds together all those, well, multiplies and adds all those guys together. So what happens if, as instance, the R's are 0, 1? What you're doing is just selecting some of them, some of those encryptions. And if you add them together, well, they are encryptions of 0, so the addition is going to be an encryption of 0. So now that you have a random encryption of 0, you will add to this random encryption of 0 your message plus some error in the B part and some randomnesses in the A part. And the result, if you solve the math, or again, you trust me, is going to be a LW encryption of the message M. And to encrypt M, you didn't need to know the secret key, but just those encryptions of 0. Okay. Yes.
Do you need like to, so the length of the public key is fixed. It just depends on lambda, right? And then essentially every time you want to encrypt, you recombine this public key elements to get one of the exponential and many public keys.
Yeah, you every time you do an encryption, you re-randomize the R's and you recombine and you produce a new encryption.
My point is like there are K is about lambda, and then the space of public keys is exponential. This is my question. K is like about lambda, right?
I think K, I don't remember. I check periodically how much is K, and I constantly forget how much is K. I think it's N times a small factor, if I remember correctly, but I would need to double check. It's a little n times a small factor.
Is your lattice dimension? What's that? Sorry.
N is the size of your secret key.
This is lattice dimension.
Yes.
Okay. That's me.
Yeah, again, I don't remember exactly how much is K, but I think it's N times
not linear. I'm happy. It's not linear in the number of operations you need to do. I'm good.
No. I think it's independent from the number of operations you have to do. Yeah. But again, I don't remember the exact amount. I can double check. I do it periodically. I forget. That's how it goes.